Hello. Today's lesson is on half-life and radioactive dating. Half-life is when the time it takes for half of the mass or the radioisotopes, something unstable, to decay into something that is stable. So you'll recall from Earth science, we'll have an unstable parent isotope, that's the radioactive isotope. And that's unstable because it has too many neutrons or too many protons. Something in the nucleus is making it unstable. It's going to decay to a stable daughter isotope. A daughter isotope is what it turns into when we think of transmutation. So it's turning into something different, it's transmutating into something that is stable. And then you can use that knowledge and apply it to radioactive dating, which you remember things that are pretty recent geologically. You would use carbon dating, something very, very old, like you're checking a specimen brought back from the moon from our Apollo missions, or you're checking rocks at the base of the Grand Canyon. You'd be using uranium dating. So something older, different isotope than something younger. So half-life is the time it takes for half of the radioactive material to decay. So we're working in proportions of half. Something, it goes half to a quarter to an eighth to a 16th. We can do those proportions pretty easily. So the typical radioactive decay curve looks like this. I just discovered this cool pointer. Whee! So if we started off with a 10-gram sample of strontium and it went through one half-life, what's half of 10 grams? 5 grams. So 5 grams would remain after one half-life. Now you can then test and see how much time did that take. Well, it took over 25 years. So we know that the half-life is 28 maybe. Then if you have another half-life, so we had one half-life, then a second half-life. So what's half of a half? A quarter. So a quarter would remain if we were using fractions. And then we have that time again. 28 times 28 is maybe, what is that, 64. So we can look at the time it's taking. A third half-life, half of the half of the half. So what's half of a quarter? An eighth of it, the sample will remain. And then at a fourth half-life, we have a half of a half of a half of a half. So we just keep doing that proportion. And when we think about half-life and radioactive decay, the radioactive isotopes never really go away. You can't get to zero. You just keep cutting things in half. You will get to something that is statistically insignificant, but you never will get rid of it entirely due to this. So for the next of the things, we're going to need a calculator. So if you have your calculator with you, great, grab it. If not, get your phone and use a calculator. Open it up on your Chromebook with your calculator. But you'll have to do a little math for this. So to be able to write on this, I haven't been able to figure out how to do it in this presentation mode. I have to exit this and then go into the smaller screen mode. So I'm just exiting that, and I'm going to click. Whoa. What's happening there? No, I don't want a movie in a movie. Oh, there I am. Hi. I actually don't need that to do this, so I can unclick that, I hope. There we go. Bye. So a sample of radioactive substance with an original mass of 16 grams was studied for 8 hours. When the study was completed, only 4 grams of the substance remained. What is the half-life? So like all problems, what we should do is look at what's important. The important things here are we had a mass of 16 grams and we looked at it for 8 hours. When the study was completed, only 4 grams of the radioactive substance remained. So just the radioactive part. It's not like things disappeared. It's just they transmutated into something else, something stable. So we need to figure out what is the half-life. So I have a method it's not the most scientific method, but it's the most common sense, easy method. You'll see in Tyler DeWitt's video next is probably a better method. But what we do is we're starting off with 16 grams. You take the amount you're starting with, and then you take your ending amount. So you have your start amount and your end amount. We're ending with 4 grams. And we want to figure out how many half-lives took place. So what is half of 16? Half of 16, my math wizards, you're all out there shouting, it's 8. So 16 grams of radioisotope. In one half-life, you'd have 8 grams of radioisotope, and you'd have 8 grams of stable daughter isotope. You'd still have that same conservation of mass, same mass. Then we have a second half-life. That gets us to our 4 grams. So in our first half-life, we cut the original amount of radioisotope in half. So 16 grams to 8 grams. Then in our second half-life, so from 8 to 4, that's our second half-life, we went from 8 grams to 4 grams of radioisotope. So in this case, we went through 2 half-lives to go from 16 grams of radioactive isotope to 4 grams of radioactive isotope. In the problem, it says this took 8 hours. And what is the half-life? So if it took 8 hours to go through 2 half-lives, what is 8 divided by 2? 8 divided by 2 is 4. So the half-life of this substance is 4 hours. So for each half-life, in 4 hours, half of the radioactive isotope will have decayed into the stable daughter isotope. So our next questions are some multiple choice questions. You're going to need your calculator, and you're going to be able to do this. How much time must elapse? What does the word elapse mean? Elapse means how much time goes by before 16 grams of potassium-42 decays, leaving 2 grams of the original isotope. So they're pretty specific here. They're telling us our radioisotope is potassium-42. So you're going to look on table N of your reference table. So go ahead and get table N. So I had to pause for a sec because I had to go get my table N. So if you go to table N and you look up potassium-42, that'd be K42, you'll see that the half-life is 12.36 hours. Now, according to each of these choices, we rounded it to 12.4. So if the half-life is 12.36 or rounded to 12.4, we can figure, all right, what's going to be our total amount of time? So to go from 16 grams to 2 grams, let's set up our chart. 16 grams. We start off at 16 grams. What's half of 16? 8. So that's one half-life. 8 grams of radioisotope will remain. What's half of 8? 4. So after 2 half-lives, 4 grams of radioactive isotope remain. What's half of 4? 2. So that would be in our third half-life. So after 3 half-lives, we've cut 16 in half to 8, 8 in half to 4, 4 in half to 2. That takes 3 half-lives. If one half-life takes 12.36 hours or 12.4 hours, then 3 half-lives would just be this equation. You take the total time, or the half-life time, multiplied by the number of half-lives, and it gives you the total time that you have watched the decay. So our answer here is choice C. So for the next one, I'm going to have you pause the video, you try to solve it, and then we'll see if we match our answers. I paused it too soon. I actually have to go to the next one first. So here we go. All right, so based on reference table N, what fraction of a sample of gold 198 remains radioactive after 2.69 days? Use table N, look up gold 198, and figure out the half-life. Pause it, press play when you're done. So gold's half-life is 2.69 days when you look it up. So one half-life takes 2.69 days. That D stands for days in our reference table. So what fraction of a sample of gold remains radioactive after 2.69 days? So if this is the half-life after 2.69 days, how much of the sample remains? Did you pick A, B, C, or D? Hands up for B. It's a half, because you start off with a whole sample. Like, say you had a piece of paper, nice rectangle, and in 2.69 days, half of that paper becomes stable. That means that, oops, my scribbling isn't very good. All of this that I've colored in down here, this has become stable, the stable daughter isotope during that 2.69 days. So that leaves 1/2 remaining radioactive, and it took 1/2 life. Same thing with this one. Press pause and see what you can do. What is the half-life of sodium-25 if 1 gram of a 16-gram sample of sodium-25 remains unchanged after 237 seconds? So you're actually going to figure out the half-life on this one. Press pause and see if you can solve this. Press play again when you've got it. All right, you're back. You've solved it. You're a math whiz. So what is the half-life of sodium-25? 1 gram remains unchanged of 16 grams. I've been using the same number just because it's easy to cut in half. So if we start off with 16, what's half of 16? 8. There's 1 half-life. If we cut 8 in half, there's 4. That's 2 half-lives. This question's the same as the others, but just a little twist at the end. So we learn all the varieties. If you cut 4 grams of radioactive isotope in half, you get 2 grams, and it took 3 half-lives. Then we need another half-life to go from 2 grams of radioisotope to the 1 gram they tell us in the problem. That means it has taken 4 half-lives. Now, 4 half-lives is not the answer. They're asking for what is the half-life. So it says that the total time here was 237 seconds. So the whole time elapsed is 237. If we divide 237 divided by the number of half-lives that we have gone through, we will get the answer that we need. So I'm going to go to my handy-dandy calculator. 237 divided by 4 looks to me like 59.25, which rounds to 59.3, and that is B. Glad you can get those right. Okay, our next question. Whoops, I went too many. After 32 days, 5 milligrams of an 80 milligram sample of radioactive isotope remains unchanged. What is the half-life of this element? Press pause, solve this problem. Press play when you got it done, and we'll go over it. All right, so after 32 days, that's going to be the time that went by. We have 5 milligrams of an 80 milligram sample. So we're starting off with 80 milligrams. What's half of 80? 40. So from 80 to 40, that's 1 half-life. I hope I can make this fit. From what's half of 40? 20. That's 2 half-lives. What's half of 20? Uh-oh, I'm going to run out of room. 10 grams of radioisotope remain. That'd be 3 half-lives. What's half of 10? Oh, I'm going to make it. Yes. Half of 10 is 5. Hard to write a 5 with the mouse pad. That's 4 half-lives. When I bought my Chromebook, I thought I was getting the one with a touchscreen, but I didn't. So I'm writing with the mouse pad. So after 4 half-lives, 5 grams of the original 80 grams of radioisotope remains unchanged. So this took 32 days. So 32 days is my total time. And we had 4 half-lives. I don't think you need the calculator for this one. What's 32 divided by 4? 8. So 8 days is the half-life of this element. It would take 8 days for half to change to the stable daughter isotope. If 1/8 of an original sample of krypton-74, watch out Superman, remains unchanged after 34.5 minutes, what is the half-life of krypton-74? This one's just a little different because it's using fractions. Try to test your knowledge of fractions now. Press pause, solve this one, and let's see what you can do. All right, you're back. 1/8 of the sample. Well, 1/8 started off from a whole, 1. So we begin with 1, just the whole thing. That's what it represents, a radioisotope. In 1 half-life, what's half of 1? We have a half. So that would be our fraction. In 2 half-lives, what is half of a half? We're just cutting everything in half each time. What's 1/2 of a half? 1/4. In 3 half-lives, what is half of 1/4? Half of 1/4 is 1/8. And that's the number we need in our problem. All right, so we have 1/8 remaining. Took 3 half-lives. The time that it took for this to occur was 34.5 minutes. So if you did 34.5 divided by the number of half-lives, which when I count the number of half-lives, it was 3. 34.5 divided by 3 should give us 11.5, somewhere near 11. So 11.5 minutes for each half-life of Krypton 74. So this is just a way of doing math problems. You're just doing proportions, halves of halves of halves of halves. That's all. Whoops, I just moved everything. All right, I think this is the last one. Yeah, well, you don't want it to be the last one. This is fun. How many days are required for 200 grams of radon-222 to decay to 50 grams? Press pause, solve it, get it right. All right, so how many days are required for 200 grams of radon-222 to decay to 50? We start off with the total amount, 200. You're experts at this. You're already saying, all right, quick, go. What's half of 200? All right, half of 200 is 100, using numbers that are nice to cut in half. What is half of 100? 50. Unless you've been watching a lot of rap videos while you're homeschooling yourself, and you're like, no, that 50 me, famine. That's okay. Live the life. So that required 2 half-lives. So how many days are required for 200 grams to decay to 50 grams? Well, we know it takes 2 half-lives. So we're missing something here. Can you find what we're missing? Well, you should have looked at your reference table for radon-222, which is Rn-222, and found that the half-life of radon-222 is 3.82 days. So if 1 half-life takes 3.82 days, then 2 half-lives takes 7.64 days. So you're just using table and in concert with how many half-lives you've actually gone through. So with radioactive decay, we can have things that are called decay series. I'm just going to change this to full mode. There we go. The screen's going to go blank for a minute, but I didn't lose you. It's not the aliens taking over. So a decay series is it's not just that in a half-life it goes to one and done. In the decay of uranium-238, which takes 5.5 times 10 to the 9th years, uranium-238 will decay to Th-234, to Pa-234, to uranium-234, to Th-230, to Ra-226, to Rn-222, to Po-218, to Pb-214, to Bi-214, to Po-214, to Pb-210, or it could go to Ti-210. It keeps going in all these different directions in this decay series. So there are a lot of intermediary steps that really we skip over and we don't worry about. So what's the importance of this? Well, it tells us how long something becomes radioactive, or it will remain radioactive in the case of Chernobyl, if you're going to live there. In the case of using medical radiation, if they need to inject some radioactive isotope into you to check your thyroid gland, they need to know that that won't last very long inside of you. So it must have a very, very short half-life. So with radioactive dating, this is not just going out on a date and it was terrible. Radioactive dating is when you use half-lives to determine the age of something. And the ballpark ones they're always talking about is uranium-238 for really old stuff, rocks, moon rocks, and carbon dating, carbon-14 for fairly recent things like you're digging in your backyard and you find some bones. and they say, well, we're going to figure out how old this was. Or you're bought some land and you find an old structure on it, and you can actually look at the wood and find out how old was that wood. Is it hundreds of years old? Was it thousands of years old? So thanks for watching the lesson video, and I hope you learned something. The next video is probably going to clear up all the questions you had from me, and then we've got a few Google form questions for you to do so I can get you a good grade on this, and you're all set. So see you in a couple days. Bye-bye.